Okay, everybody online can hear me fine. I was just yelling at Clancy, so I'm pretty sure that's a yes.
Si, senor.
How's your back?
Broken.
Still bad?
So bad.
Well, I'd say go get a cortisone shot all in every joint of your body, but I'm not sure that's great medical advice. It's just worked for my knee really well. It sounds like magic. I don't even
I mean,
understand.
you're a doctor, so
Or I stayed in a holiday. Actually, I can't even say I stayed in a Holiday Inn Express recently. Isn't that those commercials? You see, like some guy in the street, somebody's like falls off their bike. He's like fixing their leg. Like, are you an orthopedic surgeon? Like, no, but I did stay on a Holiday Inn Express last night. There's got to be something like, how can I go from not being able to walk on that leg to like they put a shot in the joint and I'm like fine. There's something just unnatural about that. That should not be how it works. All right, so starters. Remember, this week, Thursday and Friday, no classes. It's fall break. The university is officially strongly giving guidance to stay on campus and not travel in an effort to uh, keep there from being like a mass exodus from campus, and then bringing possible stuff back. But again, that's just guidance. It's not forbidden. So if you were planning on going home or wherever and decided that's what you want to still do, you can. Um, let's see. So that's this Thursday and Friday. I think any classes that start after 4 p.m. Wednesday are also not supposed to meet. But if for some reason, this probably doesn't apply to any of you, but if for some reason the class that you're in is a graduate level class, then it might still meet since they don't follow the same calendar. They don't have a fall break or something like that. So just an FYI. So if you're in doubt, ask your teacher. So our exam will be during class time next Tuesday. The exam will be on Blackboard. It will open at the beginning of class. It will close at the end of class. I will be available, so we won't be on Zoom. We won't be sitting here in the classroom, but I will be live and available during class. So if you have a question about the exam, you can ask it on Slack. It might not make sense, but I can jump on a quick Zoom call if you want me to clarify something. But punchline is I will be live in front of a computer during the exam in class in case you have a question. I don't anticipate that being something you'll need to take advantage of. I think the questions should be relatively straightforward. The exam is my usual 10 questions. Questions designed to take about an hour, but you have the full hour and 15 minutes to do it. Hopefully, time is not the constraint for the exam. So I try to make the exam so that isn't the issue. Um, there will be one conversion question, as always, on my exams. Every exam you ever take with me will always have a conversion question on it. So that should be, going from one base to another. So, decimal to octal or octal to hexadecimal. It would also be fair game to ask a question like something dealing with file size, bits and bytes and that kind of stuff. So, for example, if I asked you, let's say you had a 300 megabit per second internet connection and you were downloading a 2 gigabyte file, how long would it take? Something like that. So, for example, just as a quick refresher, if I say you have 300 megabits per second internet and download a 2 gigabyte file, how long? Well, you can convert the gigabytes into megabits if you want. So that would be 2 times 8 gets you 16 gigabits. times 1024 gets you megabits, divided by 300. Hold on. Times 1024 gets you megabits, divided by 300 gets you 54.6 seconds. So that's 2 times 8 gets you gigabits. Then times 1024 gets you megabits. So this is 54.6 seconds divided by 300. Get you that. Make sense? So those are things you should be comfortable with as juniors or seniors in computer science, going between bases and also knowing about bits and bytes and megabits and megabytes and all those things. So there will be one question involving one of those types of things, as there is on all of my exams. All right, so there will be a total of 10 questions. So there will be at least 5 programming questions. And this could be write your own code or read code and tell me what it does. There will be 4-ish short answer / essay questions. Now, I could also have you look at a grammar and give me an example of something that fits that grammar. So you should be able to read grammar. So for example, maybe read a language grammar. So if I showed you the grammar for lambda calculus expressions and said, show me, write a line that fits this grammar, you would show me something like, lambda AA. Technically, that would meet the, lambda open parenthesis, A close parenthesis, and then A. That would technically fit that grammar. Something along those lines. Okay. So what I'm going to do is I'm going to go back through the slides and kind of point out things that are going to be extra helpful, and then we'll keep cooking with our current interpreter. Now, a couple things I'll throw out there that you might find handy for kind of studying for the exam, especially the programming questions, is going to be like some of those, the early assignments where it was like little puzzle things, like write duple or swapper and those kind of things. So I would probably ask you, several of the programming questions will kind of be along those lines, working with catters and cooters and that kind of stuff. There will be questions dealing with the more interpreter type stuff, but sometimes those are hard to ask, like since it requires some like parts and you only have an hour and 15 minutes to take the exam. So it might be more of list manipulation type puzzle-y type things to kind of show that you've done enough of this work to become competent with scheme and that kind of stuff. All right. So certainly understand the difference between an interpreter and a compiler. Because when here we're writing interpreters, and that has connotation with it, that it's something that runs during runtime, and that's how we're writing these with cons to determine which grammar element we are matching. So, I don't know if I'd write I don't know if I have a question specifically about interpreters, but it's certainly something that you should understand that that's what we're working on in here. So I probably wouldn't ask you regurgitate this slide, pros and cons of an interpreter. Let's see. Definitely be familiar with variable environments. If I show you a extend env grammar-based environment, you should be able to tell me what a variable will resolve to or something like that, or write some code that operates on that kind of environment, something like that with a cond. So you should be familiar with scheme at this point, very comfortable using lists, very comfortable using cars and cooters and ifs and cons. So, the idea here is that, scheme is a fairly simple language. There's not a whole lot to it. With that in mind, you would, that shouldn't be it should be something you've already kind of accidentally learned. You shouldn't have to go and memorize those things. Recursion is something you should definitely be familiar with, and pretty much every question on the exam dealing with coding will probably have you do something recursively. That's been something that hopefully is starting to become a little bit more comfortable for you. Certainly the difference between append and cons, that how append glues two lists together where cons builds a list. That would be something you should definitely understand for working with some of those little puzzle things. Let's see. It would be fair for me to ask you to write a grammar that matches a certain type of thing. Like, here's an example of, a grammar for decimal numbers, 1 through 9 followed by 0 or more 0 through 9s, something like that. I'm not necessarily going to be looking at like the formal grammar syntax, whether you do it, with the vertical bar ors or having on multiple lines, but really, can you describe unambiguously a language? If I say, here's our, like right now we're doing lambda calculus expressions. So if the language of lambda calculus expressions that we keep expanding on, let's say that we go back to the original version of that just had 3 productions, our var expression, our lambda expression, and our app expression. I should be able to ask you to write a grammar that mimics a different language, like the language of binary trees, for example, is what you did on the lab thing the other day. But you should be able to write your own for something simple. It wouldn't be anything crazy, but, some pattern that you should be able to describe, reverse engineer. What does the grammar that describes this type of thing look like? Okay. Obviously, definitely be able to work with lambdas, understand that lambdas are first class expressions in a scheme, meaning that you can pass them as parameters to functions. So, you should be able to read code that, has lambdas coming in as parameters and applies them to something. You should also be able to write that, although I wouldn't ask you to write something where you would not be allowed to create helper functions. So if you prefer to write helper functions and then call them from within things as opposed to pass around, simplified lambdas, that's okay. I'm never going to say you must do this without writing helper functions. But it's possible if I show you code and ask you what this does, I might not have a helper function. I might embed a lambda in there, and you should be able to work with that. Definitely be familiar with map. We haven't used it as often recently, but we used it earlier on, and map is something that I could certainly put in one of my code examples, and I might write ask you to write code that might be easier to write using map. I don't think I would force you to use map in a question. So I don't think I would say you must answer this using map. If you wanted to take the longer route, you could. That just will cost you time. Go ahead.
I'm assuming for like stuff you would write, you don't want us running it.
I mean, in general, I would say no, but hey, I don't necessarily care. You're only hurting yourself or something. I mean, I'm going to grade this stuff with, the understanding that maybe you didn't run this, so you might have a missing parenthesis or something like that. You know, but I also want to see what you're capable of. So if, you know, you're working on something like, oh, well, what does that function do real quick? And you want to just test it in Scheme, that's fine. You know, I would say if you can look yourself in the mirror and say, I didn't cheat, you're probably fine. I'm not going to sit there and go and look for, you know, two people's things looking the same or something like that. So, I mean, you know, there should be, you know, closed note, closed book. If you want to use something for formatting or whatever, like you want to use Dr. Racket, so it gives you your closing parentheses and things like that, that's fine. If you really want to run it, I don't necessarily care. That just gives you the peace of mind. It's also just going to take you time if you have to go back and fix stuff. You know, my presumption would be that you're not going to spend time running it and debugging it, but ultimately I want to see what you're capable of. So if you only turn in half an exam because you didn't get, you know, the rest to it, then that probably is not going to be as good for you as if you gave it your best shot without running it and got to every question and something like that. But, you know, don't work in groups, but if, you know, again, I'm not going to sit there and police it. So, you know, do whatever your conscience allows, I suppose. All right. Yeah, I mean, this would be like an example of like a grammar that, you know, a list of integers can be the empty list, or it can be a list containing an int followed by a list of integers. You should be able to write those kind of things. You should be able to read those kind of things. I probably won't ask you vocabulary terms, stuff like that, this whole thing's a grammar, this is a production, this is a production. I might reference them like that. I might say, you know, given these, you know, which of the three productions is, you know, matches the below code or something like that. But so you should know when I say production, what I'm talking about, but I won't ask you to like define production or something. Also on the exam, if I reference any of these things, like what's an S list or something, I'll give you the grammar. You won't have to memorize, you know, these stupid grammars for our examples from the code. You should know like what symbols are and those kind of things. But if there's a grammar I want you to operate on, I'll give you the grammar as a as part of the exam. The concept of occurs free versus occurs bound, that would be fair game if I, because this kind of deals with variable binding. If I asked you to write a lambda calculus expression that shows a example of a variable x occurring free, or a variable x occurring bound, or a variable x occurring free and bound, that kind of stuff, you should be able to write those things. You should understand the concept of something occurring, for starters, where things occur versus where things are bound. All right. I mean, technically you should be capable of writing occurs free or occurs bound, but I probably wouldn't ask you to write that on the exam just because it's a little bit longer. Will take more time, but I mean, it's not like it's a complex thing to write. It's just a time thing. So I probably ask you to write things that are maybe a little shorter. Yeah, so I mean, if you're going through and practicing for the exam for some of like the scheme competency coding questions, going through like some of these old ones would be kind of good things. So I think you should probably find them to be many of them at least, to be pretty easy now. You know, a lot easier than it would have been when you did your first pass through them, something like that. Certainly the concept of a predicate, you know, if I reference, you know, the word predicate, you should know what I'm talking about. You know, I'm not going to ask you to define predicate, but you should know that I'm effectively talking about a test function for testing whether something matches something else. And we've written a bunch of those now with our, now that we're into our interpreters. All right, so again, keep going through these guys. I would say that for the exam, the kinds of questions I would ask for the programming ones would probably be 1 and maybe a 2-star question. So I would say most of them would be 1-star questions with maybe a single 2-star question. terms of complexity of those questions, because I'm going to pay attention to how long it should take you to write, so that you have enough time to answer every question. I don't want to have a half-written exam because you didn't have enough time to get to stuff, unless you just don't know the stuff, and that's why you couldn't get to it. So I'm going to pay attention to how long things should take. The whole concept of variable binding and how that relates to, in our Lambda calculus expressions, related to our environments. When we bind a variable, that means our environment modifies, and then the body of a Lambda then gets executed, applied within the newly expanded environment, that type of thing. So understand, now that we've gotten into our interpreters, the relationship between the variable environment and our code executing, because we're actually seeing parts of programming languages that we've been dealing with for several years now, where you have variables that have been defined within some scope, even though we haven't started talking about implementing individual scopes because we haven't written functions into our language yet. The whole idea that a variable binding means a name value pair being appended in some way onto our environment, whether we use our current extend-env model or have a new invention of what our environment looks like, doesn't really matter. Just, that's where binding occurs, and then code is executed within the context of the current environment. So more recently, we've gotten into this idea of an abstract, more recently, we've dealt with the idea of an abstract data types, where we dealt with that successor and predecessor stuff. We did it with our bidgets, right? But the idea is that, how do you calculate a 3? Well, you take the successor of 0, you take the successor of the successor of the successor of 0, and that gets you your 3. So that kind of idea of dealing with things in terms of the abstract rather than hard-coded values, where you can calculate for a value as opposed to having to have a whole bunch of stuff built into, in our case, our language. We might have the assumption that all of our literal types exist, but now just recently we've added that to our language to be able to represent literals. But even within that, we've decided that, we'll just go ahead and keep it easy and say, well, numbers exist. So we'll allow you to just say the number 3 or the number 4 or the number 5. But the reality is those things only work because Scheme supports those. If Scheme did not support those, but Scheme supported math and Scheme knew about 0. So if all Scheme understood was 0, could you represent a 3 or a 4 or a 5? Sure, you could do that abstractly through successors. Successor of 0, 0, successor, the successor, the successor, the successor of 0 will get you to that level. All right, so that concept, even though we're not really writing that, because at some point that just becomes kind of a this sucks type of thing, but understand that idea of abstract data types is important when we can't necessarily rely on our language having things that we sometimes take for granted. So for instance, addition. This idea of addition can be done in terms of without using a built-in math function. You can represent it using your idea of successors and predecessors. All right, so this is our environment interface, be able to work with environments. If I say, using our extend-env grammar, create an environment that has A equals 7, B equals 14, C equals 2, you should be able to show me an example of a legal environment that has those in it, where you extend the the empty environment with one of those pairs, and you extend that environment with another pair, and you extend that environment with another pair. Be able to create representations given a grammar. The idea of extractors, I think will be on there in some form, where I might give you a grammar or give you some, well, probably give you a grammar and say write extractors for the 3 components of one of the productions, something like that. So for a Lambda, if it was a Lambda, your extractor might be for the bound variable and then the body. Those might be your 2 extractors for that one production, that type of thing. The idea of parse versus unparse, unparse expression, why do we need to parse it? How do it takes us from our syntax, our preferred syntax, into our logic for our interpreter itself. Gives us the ability to have syntax that maybe looks more interesting or something like that.
So this is kind of off topic, but when you wrote the dice roller in the chicken language, is that how you did it? You essentially wrote an interpreter that would parse it into the chicken language through Python?
Right. Yeah, because this was what he's referring to is last Christmas on my cruise, I used this language called chicken, who all of their functions are based on a certain number of chicken calls. Like chicken is one function, chicken is another function, and so on and so forth. So you can imagine that makes you pretty crazy pretty quickly, right? So I wrote an interpreter or a parser really that allowed me to say, this is what I want to say. Give me the proper number of chickens for this so I can make that function call. So I wrote an interpreter that interprets from human to chicken to write efficient, well, to more mentally stably write chicken code. I guess something like that. Yeah, so that was kind of an interesting example. Okay. So that will be the stuff that's covered on the midterm, up to the stuff that we've been dealing with more recently. So I mean, if we go and look at our interpreter right now, this idea of, our environment, our constructors for our grammar, all these things are fair game. I wouldn't ask you to memorize this though. So anything that I wanted you to use, I'd give you, or I'd give you a grammar and ask you to do something. So it's not that you have to go and memorize all of our different constructors and stuff here. But if I gave you a grammar and I told you to write a constructor for the 3 productions of this grammar, let's say we had the simple lambda calculus expression, that had our var expression, our lambda expression, our app expression. I say, write a constructor for those 3 productions, or write a constructor for the second production, something like that. You should be able to write that. You should know what I mean by write a constructor. The thing puts it into a format that we can then use. Similarly, you should be able to write extractors. You should be able to write predicates for those things. So maybe I give you a production, I say write a constructor, a extractor, and a predicate for this grammar. Something like that. That's something you should know what I'm asking you to do by those words. Okay, so questions about the exam? Anything you want me to go over? Or... review. Okay. So then let's look at our language here. So we were adding what for our, so I'm guessing I put it on, did I put it in my interpreter? Oh, this ask question. So this was the thing to write for the homework, this last part. All right, so ask question, that's our version of an if statement here. So this is going to, so if I kind of, rewrite this a little bit, this is a list containing ask question followed by a Boolean expression. That's the question I'm asking, followed by the verbiage that says if true do, followed by the expression that we will execute if it's true, followed by the verbiage if false do, followed by the expression we should execute if it's false, right? All right, so we need to go ahead and I'm actually going to steal this so I can reference it as we're going through here. So we're going to go ahead and create our constructors for this. So the pieces of information that we need for a ask question expression. So we'll say define ask question expression to be a lambda, and this guy is going to need what? A Boolean expression, a true expression, and a false expression. Those three things, that's what we're going to need to build it. So we're going to call this guy, he's going to take in a Boolean expression, a true expression, and a false expression. And he's going to create a list with ask question expression at the beginning of it. Then it's going to take our Boolean expression, our true expression, and our false expression. So that's what our constructor is going to look like for that guy. Oh, hold on. I already built an if expression. Oh, okay. So we already have if expression. We already have if expression to Boolean expression, if expression to true expression, if expression to false expression. So we have those. So we named our underlying interpreter, we called it an if expression, even though our parse expression is going to have our ask question. Got it. Predicates, we have an if expression for that. Did we already write our extractor for question expression? We did. So here's a question expression to test expression, question to true, question to false. So then for parse expression, this is where we have not written it yet. Okay. So we'll have equal car of our code if it's equal to a ask question. Then what are we going to do? We're going to build a if expression. And our if expression is going to take in a the Boolean expression. And how do we get that? Well, we need to extract that from our so we're going to have our test expression. Actually, what we'll do is we'll go ahead and just call parse expression on the first part of that. So we're going to use our constructor for if expression, which takes in 3 parameters. One is going to be whatever parse expression returns for the Boolean portion of my if expression. And that guy is called question expression to test expression. code. I'll call parse expression on that. We'll call parse expression on, I guess it's just called true expression, right? Our code, and then false expression. So that's our constructor for if expression. And that will give us our output for that. If it looks reasonable. So that's what the homework was, to write that. Oh, then fix apply expression for that. Got it. All right, so let's make sure we get a good parse expression on this guy. Did I already write some stuff for my question? Here, we'll steal this guy. All right, so we're going to write a ask question, test less than, get value, literal. If true, do one. Okay, so I think that should be a legal thing. So we'll call our parse expression on this guy to test that. And we will comment that out for right now. And let's make sure we get what we think we should get out of that. An extra D? Oh, that. Is it probably the same thing in the false expression? No. So this gives us if expression. Here's our Boolean expression, less than, var expression, lit expression, lit expression, lit expression. Okay, it looks like it parsed it correctly. So now you're also supposed to update apply expression to now work for if expressions. So we have an if expression, lambda calculus expression. If that's what we're dealing with, then we need to do our test. So we could probably do this inside of a let to get our individual pieces. So we'll go ahead and say a let. We'll call this guy bool result. And we'll have him equal apply expression. And he's going to equal apply expression on what? We need to get the if expression. Is that what we called it, to test? This is for coder extractor. To bool expression. I'm lost. So if expression to bool expression of our lambda calculus expression. and we're going to apply that in our current environment, right? So that's going to give us our result for that Boolean expression. Now, our Boolean expression does boil down to true or false now. So we can use that as a test. Now, we might be, in fact, I'll actually go down through the this process. So let's say that I'm going to say true expression. And I'll actually go ahead and write this. We're going to say if expression to true expression, lambda calculus expression. So that gets us our true expression. Our false expression will be if expression to false expression from our lambda calculus expression. Now, just for a moment, I'm going to change this to a let star. That way I'm allowed to do what I'm about to do. I'm going to say true result is equal to apply expression on true expression in the current environment. False result is equal to apply expression on the false expression in the current environment. Why is this part a bad idea? Give me some, well, there, the given information is it's a bad idea. So given that it's a bad idea, give me some reasons why it's a, might be a bad idea. What's some downside to what I'm doing there, where I'm actually calling apply expression on the true expression as well as on the false expression, anticipating, here, we'll just actually finish this thing and we'll do something like, well, if bool result, then true result, else false result.
Because you're processing a whole part of the expression that you might not have to.
Okay, so that's a reasonable start. So I'm possibly being inefficient, right? And well, I'm not even possibly, I'm definitely being inefficient because I know with an if, I only will do one of the two, never both, correct? So I'm guaranteeing in this situation that I'm going to be processing the at least one extra thing that I won't need. Okay, so I think we're down a good path there. What else might be, why else might this be a, that's my quest too. Why else might this be a bad idea? Go ahead. Possibly, yeah. Probably not in our, what he said is, could you mess up your environment if you did that? Probably not in our current case, as we don't have the ability to do that. But if we're kind of looking forward, we're probably going to want to be able to add stuff to our environment. There could be an issue with breaking our environment by doing something that we wouldn't have otherwise done. That's true, something to be concerned about. Go ahead. Well, they're going to still see the beginner. The result, I don't think is going to make a difference because we're only going to show them the result here, the result here. And I think they would write it the same way. Oh, I see what you're saying. Possibly. Yeah, that has more to do with your concern about this line, right? That maybe this line needs to be a little bit more thoughtful. something like that. Yeah, so that's true. We'll talk about that in a second. That's possible. We might want to think about how the output is framed. But this stuff up here, what else is problematic with those two things? We're kind of dancing all around it right now. We've said everything we've said so far has been accurate. You know, we're definitely wasting our time with one of those, right? We might have some environmental issues down the road, depending on what we decide to do with our environment. Anything else you can think of? So let me show you a Java example here, maybe. Actually, I didn't even do that. I can use my Bible book stuff I have here. Something like that. Yeah, don't worry about the red underlines here. Assume it lets that go through. So I have this object named B. Now I'm asking the question, if B is not equal to null, that's my test expression, right? It's my Boolean expression right here, B not equal to null. If I go ahead and I apply expression for this one and apply expression for this one, before I actually ask the question about whether this was true or false, what's going to happen in this situation? Well, this would be an error, right? If I said b dot get name right here, it's going to yell at me and say the local variable b may not have been initialized. Well, in this case, I purposely didn't initialize it, right? So I know it's equal to null right here. So now I'm asking, well, if it's not equal to null, go ahead and call a function on it. Otherwise, call a different function on it. So this is now me calling null dot get name, which is going to be very bad. I'm going to get an error, program's going to crash, all that stuff. So the nature of an if indicates that one of those Boolean, or one of the true or false expressions, probably the false, won't work. Well, actually, no, I guess it would be probably the true. The true won't work unless the Boolean expression boils down to true. So I can't pre-call it until I know I'm allowed to call it. Because if I call it without knowing I'm allowed to call it, I might run into null pointer exception, something else. That's the whole reason why I wrapped it inside of an if, where I'm going to say, hey, I'm only going to try to start my car if there's gas in it. Right? Something like that. Or maybe the better thing, I'm only going to try to start my car if there's oil in it. Because then starting the car could have a negative impact on the actual vehicle if you don't have oil in the vehicle, right? There's kind of our real life example of why we might not want to do something like that and pre-call those things. And all the other things you said are accurate as well. So there are several concerning reasons not to go down that path. All right, so we're going to go ahead, we're going to take those couple of things out of there. Now, are we safe doing these two things though? Can we just pre-extract the true and false expressions so that we're kind of prepared to evaluate them in a second when we need to? Yeah, that's fair enough, right? All right, so now we'll ask the question. So we have our expressions that we're going to want to. We know, as Noah said, we're only one of those is going to fire, right? So we already have the two expressions extracted just ready. Now, maybe along Noah's point, we can say, well, you technically extracted one you didn't need to extract. That's a true statement. But maybe we say, not a huge deal. It's just one variable here, and it's going to make our code in here look a little cleaner. All right, so now we'll say, well, if our Boolean result is true, so if that's true, what are we going to do? Actually, I'm going to do this. Then we'll go ahead and call apply expression on our true expression in the current environment. Otherwise, we'll call apply expression on our false expression in the current environment. And that will be our result for our if expression, which, to your point, maybe doesn't necessarily give us the friendly output we might want. We can just decide on that on the other side, but I think it does give us an accurate output. So now if we go down here, and I'll go ahead and comment this out, but we'll go ahead and run our if statement here. We're asking a question whether the value of A, which does not exist, is less than 7. So is 4 less than 7? It is. Then we will boil down to a 1. Otherwise, we'll boil down to a 0. So this should give us a 1 in. So there's our 1. If I change my 4 to a 40, this will give us a 0. So that's our output for our true, false, whatever for this. And that's probably okay for now. I mean, that's what we said to do when it was true, right? If we wanted to print something and make it look cleaner, we could do that. Okay, so now we have the ability to ask questions. Can we also ask multiple questions? So we can effectively build in, I can say, well, if it's less than A or less than 7, then for this part, we can ask another question. So if it is greater than 5, boil down to 1, otherwise boil down to 0. Here, I'm going to kick this down a line here. I could have kicked it down a line a lot earlier than that. We only currently know how to do literal numbers, so that's why we're we're leaving it at that. Although actually, it doesn't work for anything because we're just boiling down to the literal. So we actually could do symbols or something, but so we'll leave that at 0. So now we're asking a question inside of a question. So if A is less than 7, then if A is greater than 5. So really, we're asking is if A is 6 is what we're asking here. then boil down to a literal 8, otherwise boil down to a literal 9. But if this first part is false, we're just going to get a literal 0. So right now it should still be a 0 because I have my A as 40. But if I modify A in my environment, and let's say I make it so I'm asking, is it less than 7? So I'll make it a 4. So is it less than 7? Yes. But is it greater than 5? It's not. So now I'll get a literal 9. So now if I change it to be exactly a 6, now I'll get my literal 8. So that kind of creates the existence of an and, correct? If two things are true, I can now do this. So there's my 8. Make some sense? Okay, so we now can ask a question. We have an if statement. So we have an environment for representing variables, so we can remember things. We have the ability to ask questions through our conditionals. What else? What's the next thing that all programming language should be able to do? Repetition, some kind of repetition. Because right now we're by the Lippmann definition of 100% of programming languages should be able to remember things, ask questions, and do repetition. We don't quite have a programming language yet, right? We almost have a programming language, but now we need to actually have a programming language. All right, so we're going to add some repetition to this guy. Now, and this is something we see in some of our modern programming languages where I think it's sometimes gotten a little bit out of control. We've seen it with somewhat with Python. I think we've definitely seen it with Swift, where Swift gives us 4 zillion different ways of writing loops that match every possible loop syntax from every possible language that's come in the history of programming languages. And then you can use, you have a variable with the poop emoji. I already made fun of that in here, didn't I? That's ridiculous. You can use emojis for variable names. So in any, and then we said that was like hieroglyphics. It's going full circle. Does anybody know how to actually read emojis? Like, is there an official emoji language, or is there nuance with emotion and stuff? Like, there is nuance, isn't there? Like, if somebody gives you like the cryy face, that can mean a lot of different things in like context, right? It can mean like they're laughing so hard they're crying. It can mean they're sad, all sorts of stuff. Keep making the same mistakes. So emojis don't make sense for variable names. We learned about this in 2004 when we saw the Alien versus Predator movie, which is what I watched last night. They couldn't read any of the hieroglyphics. They didn't know they were walking into danger. They didn't know that this was the hunting ground for the aliens versus predators. Bad news bears. They had to blow the whole place up. Now we're doing it again with Swift. How did Lippmann mash up aliens versus predators in the Swift programming language?
Will that be on the exam?
It will be. In fact, now the entire exam is aliens versus predator. I watched over the weekend, I've been going back and watching. I mean, any of you ever see the original Predator movie with Schwarzenegger? It was way before you were born. It was like 1987. None of you were alive in 87, were you? Oh, yeah. And Apollo Creed was in it. You actually, so here, and this is appropriate given it's an election year. In the original Predator movie in 1987, you had 2 future state governors, Arnold Schwarzenegger and Jesse the Body Ventura. Minnesota state governor and California state governor. But the thing is, that movie really held up pretty well. The CGI and stuff, I doubt it was CGI. It was probably people with like paper mache back then. But I thought it was pretty good. It was definitely better than Predator 2. Danny Glover, that wasn't any good. What it was missing, it's Schwarzenegger. Love that guy. Okay, so we need loops. How did we get to Alien versus Predator? It was we started talking about loops, and then how all other languages have these different things. So we need to decide what's our the first loop or first repetition thing we should have in our language. Because when we think about repetition, it's like I want to do something some number of times. Well, I might want to repeat something some number of times, right? So now, what are the types of things we might want to repeat? At some point here, if you think about your basic programming languages, they all have the ability to print something, don't they? Okay, we don't quite have that little magic trick yet. So maybe we go ahead and throw that in real quick, just allow us to just print something, print the result of an expression. You know, we're currently getting the result of an expression, but we're not printing the result of an expression. What is the difference? This kind of goes back to this idea of when we first learned how to write functions in CSC470, the difference between a function that boils down to a value and a function that displays a value. Because there is a difference as to whether or not we can use the value versus not be able to use the value. Okay. Now I do think if we want to create, I think we have a thing called display. Okay, it does show us something different there, but there's is it print? There is a syntax in Scheme that kind of creates a box around something for when you display it. Anybody bump into that at some point? I just want to make it, I mean, right now it looks like the difference is that it's in purple if it was displayed and it's in blue if it was resolved. So if I just say 5 here, it's in blue. So purple means it was printed to the screen. Blue means it was resolved. Does anybody know what the function is for displaying something in Scheme? Let's look it up real quick. Scheme, display to screen. Oh, did I try display? Oh. Maybe right. All right, we're gonna abandon it. So purple means it printed, blue means it resolved. So we're going to leave it at that, but let's go ahead and let's add to our language a quick print statement, and then we will also so let's see, maybe for beginning programmer, which do we like better, print or display? Display. Okay, so we're going to have a display, and then we'll just say like, you know, literal 7 or something like that. And then we'll put a little note here. Note, displayed values are in purple. Something like that. Resolved are in blue. Okay, so we'll go ahead and for our grammar, maybe we call this a print expression, or do you want to call it a display expression? Do we want to differentiate it from code, or do we want to have it be the same as code? I don't know that it necessarily matters, but okay. So we'll say define print expression to be a lambda that's just going to take the value to print. Actually, we'll have it take in an expression, because that's really what it boils down to, right? So some kind of expression that we intend to print. Some expressions might not make sense to print, but So when we print this expression, we're going to create a list with print expression and expression. No laughs yet. Okay. I've embedded something for Clancy there. Alien versus Predator is going to be, we have to have an Alien versus Predator thing in the language now. It's important. All right, so we have print expression. Just going to be a list with print expression and then our actual expression. Let's get our extractors. So we'll have our define print expression to expression. This is going to be a lambda that's going to take in a print expression as a parameter, and it's going to return the catter of that print expression. And then we'll have our predicates. All right, then we need our extractors. So this is going to be our display, or define. Display expression to expression. It's going to be a lambda that's going to take in a display expression as a parameter, and it's going to return the catter of that display expression. Who what? Oh, thank you. All right, and then we'll go ahead and we're going to say equal car COD3 display. This is going to build this is for our parse expression. So we'll go ahead and build a print exp using our display exp to expression from code. Like that. Okay. Display. All right. So that's going to be my parse expression. And then for apply expression, we'll say if this is a print exp lambda calculus expression, then we will call, did we decide which of those makes the most sense? Here, we'll do write. Write print exp to exp lambda calculus expression. And we don't need to apply it or anything. Actually, we do need to apply it because this guy is an expression. What do we do with expressions? We call apply expression on that expression in the environment. Okay. So then down here, we should be able to give ourselves a So this should just display a 7 to the screen in purple. All questions were false. That's a print expression, list literal 7. Is that how literal works? The lit expression is the one that looks funny to me. And we could fix it next Thursday. So I'm not giving you homework anyways. Well, we're out of time, so let's just leave it. We must have a little bug up there. We'll leave it in there so it crashes for us next time in our parse. But this will let us print, and then we're going to probably do a repeat expression on Thursday. That'll be our first loop of doing something a certain number of times. All right, so I guess homework for next Tuesday is study for the exam. Exam will be during class on Blackboard. We won't meet here in the classroom. We're online. Just it's going to be on Blackboard during class and at the end of class, but I'll be live to answer any questions if you have questions during the exam. Otherwise, I will see all of you next Thursday. And I am around all this week, so if you have questions or need to do a Zoom to go over anything, I'm happy to do that. All right, I will see everybody next week. I'll actually go ahead and push. I think we have the updated for we're out of the bucket. What is our homework for today was what question?